back.
Okay, Suraj, this is the link for the presentation, so you can just go to the link and do the presentation. There is some accompanying code that is within the slides and referred. But the question is, why language models here? So, when Wall Street Bets was happening, Richard Gray, CEO of Numerai, posted a bounty on Leadership Day that he wants to tutorial and blog post code with exporting Wall Street Bets signal, Wall Street Bets conversation as a signal for Numerai signal. And so the data and the discussions there looks like long on this stock, long on this stock to the moon, quarter earnings bad, damn in hands, YOLO. These sort of conversations we need to convert into a signal. So within 24 hours, I was able to create a blog post and a notebook for this and submit to the initial day request, which is described in this blog post. So this is where I took all the data conversations from Wall Street Bets, trained a sentiment model for all those stocks or all those dates, and created a signal that was a valid submission. But then the question is, what language model is? Language modeling is. So, and why do we need it? So we can sort of think of languages as a human construct to describe stuff. So if you can understand language, you can understand a lot of stuff that's beneath that. So at its core, language modeling is about predicting the next word given a sequence. For example, there's a sentence, hello there, how are you doing? Today is a beautiful day. It's a Saturday. So it's say, given this sentence, what would be the most likely next word? Would be holiday? So yeah, that's at its core. We need to look at this sentence and predict the next one. And if we can predict the next one, it means we have understood the structure of that. I'd like to go from different approaches from statistical to neural networks so we can understand the language model's evolution. Beginning with the n-gram models. So this is the very basic one where we have the corpus, for example, in the next one, we have 1, 2, 3, 4, 5, 6, some few words in a sentence in a big corpus, for example, let's say a book, and we want to model those words. So the basic thing would be to make pairs. 1, 2 words together, these 2 words together, these 3 words together, and then we can calculate the probability of these 2 words appearing together. So let's say if you want to calculate the probability of word 1, 2, and 3 appearing together in a big corpus, so we can just calculate how many times this appears divided by the vocabulary. Here's the example. This is the all text in the book. I love language models. I'm talking about them today. A unigram means one token or word in this case. I love language. So it would randomly spit out the words. Background would be like we make pairs of 2. So given I, we here. So I want to take the probability of the word love given the initial word I. Same for trigram. Given these 2 words, what are the chances language is the next word? So we can model this using this formula, and it turns out we can for this sequence to come up in a corpus, we can calculate the individual probabilities, and then we can take a product of that. So how many times it's starting with I? How many times love is followed by I? How many times language is followed by love? Models, language. So this is multiplication of that. In case when something out of distribution happens, for example, I love languages and computer. So this is not part of this. So computer is a new word. So there are some tricks like smoothing and backoff that can handle 0 probabilities cases. The challenges here are sparsity. So it would take a probability big matrix, and when we see it, most of it will be 0 because there are not many pairs appearing together in a unique bit string. Fixed window size, you cannot, like, if we increase the window size, the calculation becomes so big. And overfit untuned corpus, so it's like, it's only looking at what's inside the corpus and it cannot generalize without new data. Storage, 3 grams, 2,000 words would require so much storage. Like imagine like 3 combinations of 20,000 unique words. And there is no semantic meaning. So like, this is all statistical. The model doesn't know what then refers here. Some simple applications of this approach, probabilistic approach, is next word suggestion on your phone. As you type those words, you create your corpus. And the phone's keyboard can now look at what are the most probable words appearing together. It can suggest spell correction. Now we move to deep learning. So we saw, like, we would require a big matrix of probabilities. And mostly it would be sparse. So how can we compress that or like reduce it to small vector? So instead of a big one-hot probability distribution, we move from 17,000 dimension to 100 dimension. So like the one-hot encoded, one-hot means everything at the word's location is positive, is 1, everything else is 0. So for example, in this case, if I want to represent the word I, it's like at this position it will be 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. So that's sort of index. So from that we move to 100 dimension. And embeddings are like continuous. So instead of discrete values, you can think of this like continuous way to represent those same words. Contextually aware. So this neural network proposed by Dr. Bengio. And it's taking 2 previous words and then trying to increase the probability of the correct word. So it's like a classification task at its core, but with context of previous words. And then there's this embedding, means it's reducing this dimension to 100 dimension. Yeah, one-hot encoding is like this. From this mapping, from this set, if we want to represent the word cat, it's like 1, 0, 0, 0. Unique binary representation for each word in the vocabulary. Yeah. So then there's this idea that there's some sort of semantic meaning in it. So the king word, if you represent the word king in those 100 dimensions, it would be close to queen and far from the word apple. There are those hidden layers, and the output is like the next word after the cat is on the model would say the bat is the most probable word and root and not the apple. And the softmax here, it means when we are trying to increase the probability for these 2 words, probability for other words are naturally decreasing. So that's a classification task. This is where magic happened, I would say. We could represent those words into a smaller dimension with more semantic meanings. Word2Vec is like you can transform those words into contextual numerical vectors. So the challenges with previous one model was a lot of compute. And with large vocabulary, the neural networks would increase. Inefficiency, like it couldn't naturally capture those relationships between the words. And with Word2Vec, this one was specifically optimized. So in word to act, this word was specifically designed to learn those embeddings. So here's an example. The king word is transformed into a four-dimensional vector. Man, woman, all these. And the way it's trained is, we take the word, surrounding words, like SIBO, continuous bag of words, and we try to predict the middle word. And here, given the middle word, we're trying to increase the probability for the surrounding word. So that's called a skip graph. Yeah, this is like, it has an embedding matrix, which converts this one-hot representation into a dense vector. The context window means 2 extra, 2. Negative sampling. So we want to increase the probability for these two and decrease the probability for others. So the sole goal was to learn the representation instead of predicting the next word. By predicting those probabilities, we are learning the representation. And a interesting phenomenon that happened was when you map or project those embeddings into a 2D or 3D space, this is what happens. So the representation of word king, here's queen, man, woman. So when you add the representation, so like 100 dimension for king minus 100 dimension of man plus 100 dimension of woman would be closely approximated to 100 dimensions of queen. So like we could do these arithmetic operations on word. This was great. Another thing was we could ask it like how different is it? China to Beijing, Russia to Moscow. Like the country to capital, you could map it. And so like there's like sort of similar sort of distance. And then another thing is it also kind of geographically ranking them. So from east to we go to west. So that's also a phenomenon that happens naturally. So these representations has those internal meaning. Yeah. So the applications were semantic understanding. We could now find similarity between two words, like how close they are, how far they are. So it's a quantifiable thing now. We could use it for semantic analysis, text classification, so like embeddings for a document for each word we could take, and then do classification on those embeddings. We can create another model on top of that. Search engines, similarity recommendation system, all those stuff. That came when combined with sequencing models. So like these models, like recurrence models, they can process sequences naturally. So they would take, for example, input here, and then those hidden representations are conveyed over timestamp and presented in an output. So this is called sequence-to-sequence models. They take input as sequence. This can be a time series. Price at this point, price at this point, price at this point. And now, from this hidden vector, it predicts those future timestamps. Yeah. So the LSTM, when combined with word-to-vector representations, so like we could represent sentence as a time series, as sequence, and then all those embeddings you can take and you can do a sequence modeling on top of those word embeddings. So that provides another step of classification. We could now go from word to semantically meaning sentences using these sequence models. And it could parse long documentations as well. Then came UM fit. This is posed by Professor Jeremy Howard. And this is more like, this changed things. You can compare it with ImageNet movement for NLP. So transfer learning for NLP is actually possible now after this model. Right? You could train a big bi-LSTM model that can look at both direction of the word or the sentence and tries to predict the next word. And then by using this, you can train it on a big corpus called pre-training. So we can train it on Wikipedia, all of Wikipedia. And it now understands the basic structure of the language, And then we can do fine tuning. We can just like freeze those layers, freeze these layers, and tune these layers for a specific type of text. For example, finance text. And then we can also do classification. Let's say you want to classify a sentence. We can do that using these models. This is like you take a ImageNet trained convolutional net, for example, resident, and then we freeze the layers and then we kind of fine tune the end layers for a classification task or any other task. So this is possible with UMFit. Then came attention is all you need paper that introduced transformers. So if you look at sequence models, these were also a sequence model. They have this sort of bottleneck here that this representation is encoded in this hidden layer. And now these two timestamps are encoded in this layer. These three at this point. So this becomes a bottleneck that all the information is combined into one vector. And another one was like, it was sequentially processing. So if you want to encode a sentence, you would have first word, second, third, and like it would do it sequentially, so it would also take time. Not really parallelizable. Attention is already introduced as transforming mechanism where you could do the input, and then those processed inputs would go to a decoder, and decoder would keep generating the new text. So this is like an encoder-decoder model. Encoder can take sequences, the decoder can produce sequences. And this gave birth to the models like BERT and GPT. The important part for transformer models is tokenization. So in previous times we saw the word2vec was taking the direct word representation, like word, and then its index, and then latent representation. But in this one, we kind of divide or split the big words into smaller ones, smaller repetitive chunks, and then we feed those to the model. So instead of transform a word as a whole, we feed the model the location for trans, form, and then for that there could be another one for space, for new line, and that sort of. So like Chat GPT assists efficiently. So Chat GPT assists efficiently. So this is sort of splitting and then tokenizing means giving these tokens an index, and that index of like 50,000 words will then be compressed into a 4096 or like 512 dimension. BERT is an encoder model, bidirectional understanding, like bidirectional encoder representation from transformers. So it can look at this sentence and convert it into a latent representation. The way it's trained is using a masked language modeling. So in this one, we kind of put mask in the sequence. Let's say this sentence 1. Today is a good day. So we would mask some word between is. So like it would be like today dash good day. So we want the model to predict the probability for this word to be is. So now using this, the model learns to represent those sentences by filling those masked places. And this way it learns it. And let's say if you want to do transfer learning on top of this for like say question answering. So we could be like a paragraph here, a question here, and we can just train it to predict the location of the answers here. So this one was revolutionizing. But keep in mind, this is an encoded model. It can encode the sentences. That's it. Yeah. So in this one, each word has its different meaning based on its attention mechanism. The bank and river bank, which is saving bank. So the bank the model can internally represent or like relate this bank with the river or saving based on the sentences. So like that's great stuff. And you can use it for like search engine recommendations, everything where you want to convert sentences into vectors. The second part is generative models. So, since BERT was this part only, the encoder part, and GPT is this part, the decoder only. So, you feed it the sentence, it predicts something, and it cycle repeats until it encounters end of sentence token. So yeah, GPT is, it can generate new tasks. So this is more like, we are asking it to predict the next token, and then we are asking it to predict the next token. We keep repeating this. Yeah. GPT-2 was like 1.5 billion, and GPT-3 175 billion. We don't know how much GPT-4 is. And it turns out when you scale those parameters and training data, it can get really good. So like we have seen the examples with ChatGPT that how better it can get. It can be used in daily coding assistant, content creation, anything. Let's say you want to train your own one. So you can do it in 2 steps, unsupervised pre-training. You can take all of the raw corpus, let's say the whole internet, and then you can train either an encoder or decoder based on your requirements. You could train a fine-tune a BERT to predict the max token or GPT to predict the next token. And then your supervised fine-tuning, so you want to limit the models, or like direct the model in one direction only. So you can train it again in a smaller corpus that's concentrated for your purpose. So I was doing some early experiments with this, and during COVID, I had a goal. Like I wanted to ask a question in Hindi, and there was this Sanskrit text, a lot of text, and I wanted a retrieval system that would retrieve me the documents that are related to Hindi query. So I went to the Hugging Face Hub. I couldn't find any good models for Indian languages. Well, there were barely any. So I decided to train one. So I collected all sorts of data like Hindi, Gujarati, mother tongue, and Sanskrit. Trained one multiple encoder models together, which is like this one. And then I was able to build a retrieval system that I could enter the Hindi query and could give me very similar Sanskrit text, like paragraphs, books. So, yeah. And then I also trained one GPT-2 based Hindi model from scratch, which is this one. It was all easy to train on Colab because of low parameters. Another experiment was with punctuation restoration. When I was in collaboration with VA Labs, Deterministic Algorithm Labs, there was this task of AS, automatic speech recognition. So the system would output just raw text without any punctuation. So the task was to add punctuations to them. So I tried a BART, which is a sequence-to-sequence model, a transformer based, means it can take input as a sequence, as a sentence, and then it can output a probability over sentences. So it's like a sequence-to-sequence model. I trained it one, where the input would be like unpunctuated text, and the output or the target is the punctuated text. And it was able to do it. Another experiment was with Wall Street Bets data. So like I took all the Wall Street Bets conversations, printed out the stocks, gave sentiment to these discussions, and then combined the score for all the stocks in that given day. And it turns out this is a leading indicator. For example, the price is the blue one. And the normalized transform is like the red one. And you can see the red one goes up, kind of it peaked before this one. So sometimes it works, sometimes it doesn't, but yeah, worth a try. Another experiment of this was, instead of using a sentiment model to extract sentiments, how about asking ChatGPT, like, these are the conversations for these days, give me a score, filter out the stops in this conversation, and it was able to do it as well. So like, this could be a chat, a conversation, a comment. It filtered out all the stocks mentioned in it, and the sentiment related to it, and then like a bullish or bearish. And this was great. Like, this could do word or sentences to directly sentence mapping. Yeah. And then I asked it, like, when ChatGPT had this web browsing capabilities, I just put this. It's a contract for A and B options. And it searched the web, find it, extracted information, and then below it, it also like explained what are these values and what does it mean. Another fun experiment I did was I scraped all of Numerai related data, hopefully now Peter's wiki as well in future, and then trained a Mistral AI. So initially I trained a GPT Neo X model, but since this came out, I wanted to try it, so I trained a Mistral 7B model, fine-tuned it on Numerai related data, discussions, forums, rocket chats, all the chats, docs with the permission, and then asked it, like, explain me TC, I'm too lazy to understand. And it was able to generate some structured text. And you go to this whole book, and you can fine-tune your own by like going through this. The data is encapsulated in my Google Drive, so if you want access, just email me, or you can just replace it with your own text, and it should be able to like generate. This was the initial output by Mistral's 7D model. It's a token that represents value of contribution to the community platform, incentivizes skills. This is not what TC is. But after training, it was able to understand what's that. And yeah, here's a forum post about explaining this whole process. And in short, if you want to convert sentences into vectors for your stuff, like for sentiment classification or like whatever, you can use an encoder model, for example, Word, to classify text, to cluster text file. You can even indexing and retrieval, like sensitive text. And if you want to go from sentences to directly sentences as output, you could use the decoder models, or like sequence to sequence models. For example, like GPT, that can take input as text and output as text. So you can ask it any sorts of stuff. Like, these are two examples of the same one. This is using an encoder model, and this is using a generative decoder model. Both can parse it, up to you, whichever you want to use. So in short, you can use whichever models that's suitable for your application. And here are some really helpful links to get more into depth. So my goal was to present the information, and then you can download the slides and go visit the screens and learning them. So yeah, download the slides, fine-tune your model on GoLab Pro. You can take a pre-trained one on finance. For example, Finbird is such a model, and then do whatever with vectors. Combine that with technical features. So in Signal's presentations, we saw we convert the time series into statistical features. You can now concatenate those vectors with those features and generate like 100-dimensional vectors, sentiment vectors in the data. You can train a model, that combines technical and news data for stocks. And go ahead and you can play with this model on the Interface Hub if you like to. Yeah, and this is the slide deck that you can go to and get in depth about all the topics. That's all. Thank you. Any questions?
So thank you for the presentation, Suraj. One thing I wanted to ask was that large language models are known to hallucinate, right? Mm-hmm. So did you have to like build a knowledge base or like vector database separately while you were training the Mistral 7 billion, or was it like generated on the go without any access to the knowledge base through, say, like retrieval augmented generation or something like
Yeah. So like for this experiment, I did not.
that? I see.
I just like trained one
Huh.
and straight asked it what's TC, but it would actually help to have documents index and then you. Yeah. For this experiment, I did not. But you can add it.
Thanks.
Like, is there any code sample where we can give some website domains or something and scrape automatically and do some?
But I'm not sure.
Okay.
I just manually scraped it, so like that's in my laptop, not anything.
And with script data, is there any code sample available, like where we can input the data and ask some questions and it gives some answer?
So this link will lead you to Hugging Face Hub.
Okay.
So you can go to this link and just download this model. Yeah. And to download this model, there is a link in this notebook, which is like you can just replace the model name with this model name, and it should be able to do it. And just like, yeah, play with it.
Cool. Thanks.
Any other question?
लोकल पे मुश्किल लेवल्स हैं उसमें कोलैब फ्लो पे चला फ्लो पे